said point blank, you will not have that on the test. They don't know that. Actually, they may have it. I just decided I didn't want to. And what we're gonna do. People have never heard of hyperbolic, I'm guessing, in here. So it is worth looking at some point. So if you take this equation, you get the unit circle, right? And how do we understand the unit circle? If you plug in some angle, it's sitting right here, you have a cosine value and a sine value. And you know if you do cosine squared plus sine squared equals 1. All hyperbolic means is you look at this equation. That one or this one. Put a negative sign in there. Now you get hyperbolic. And if you were to graph this, it looks like this. So for whatever input, so pick an input that lands you at this point, the x coordinate, y coordinate must satisfy this. So the x coordinate here would be hyperbolic cosine of your input and hyperbolic sine. Once you have that relationship, you can do all the trig with just Pythagorean theorem. Like if you start with Pythagorean theorem, you get all of the trig relationships eventually. It takes a long time. That's why you have a whole course on it, or part of a Raquel course. You can do the same thing with hyperbolic and come up with all the geometry facts that you need for hyperbolic relationships. The crazy thing is they work out to just a nice formula in terms of exponentials, which is not quite true here. Here you need sine and cosine. Here it ends up just being exponential type functions where you do combinations. So all the algebra actually works out a little bit easier. But you can motivate them. If you take advanced math courses, they show up a lot. And one place they show up is like if you take two towers and hang a wire between them. So like power lines. The shape of that is a hyperbolic function. So it's not quite parabolic. It looks like it might be a parabola when it's hanging. It's actually a hyperbolic shape. So in applications, we would care about this. If you go a lot further in calculus, it shows up. As far as we're concerned in here, just memorize the two formulas, I guess, or a handful of formulas. Or don't memorize, just use it in homework with the chart. The derivatives are, in some sense, simple formulas. If you take the derivatives, we're good to go. You don't need to worry about all the other facts. All right. So in this section, we've got a bunch of new rules. What is the derivative of tangent of x? Secant squared of x. So typically when you have just a trig function, the derivative is another trig function, and the hard thing is memorizing which one to do. Some of these aren't necessarily intuitive, like why would you guess that? So the big one is, or the big two would be this. What's the derivative of sine of x? Cosine of x. And what's the derivative of cosine of x? Negative sine of x. If you know those two, technically you can get all the others. And that all you ever did in trig, you knew about sine and cosine, and anytime you had like identities or all these other things going on, you rewrote it in terms of sine and cosine. You do the same thing here. So where would this one come from? So I want to find the derivative of tangent. If I write that in terms of sine and cosine, it's this, right? How can you take the derivative of that one? What's the rule? Sine divided by cosine. So bottom times the derivative of the top minus the top times the root of the bottom. All divided by the bottom function squared. And what do I get? So this one's cosine of x. What's the derivative of sine of x? We said it's cosine of x. then minus sine of x times, here cosine is negative sine, all over cosine squared x. Yeah, so this is cosine squared of x. Negative sine times negative sine is positive sine squared of x. Over cosine squared of x. Now what's the one thing we know about trig?
Cosine squared x plus.
Sine squared plus cosine squared is 1, right? So since I have cosine squared plus sine squared, that's equal to 1. So I get 1 divided by cosine of x squared. What's 1 over cosine? Secant. So it's secant squared x. Technically, if you know sine and cosine, you can get all of the integers. You would just have to do quotient rules and then simplify. Or you can just memorize it. So there are times on tests we ask things like, show that the derivative of tangent of x is secant squared x, using only facts about sine and cosine. That would be this type of derivation. But otherwise, just use the formulas that we have. But if you panic and forget one, in theory, you can come up with it. All right. So we had some of these. One more. I wanted to mention something about these. What is the derivative of inverse tangent of x? 1 over 1 plus x squared. Anything really weird about that formula? Other than the fact that I like inverse tangent. Derivative sine is cosine. So I had a trig function, took its derivative, I got another trig function, right?
It's because
What's weird about this one?
there's no trig function.
There's no trig anymore. I had inverse tangent, so that's based on trig. Took its derivative. 1 over 1 plus x squared is just a rational function. There's no more trig involved, which is possibly very surprising. It's kind of like when you take the derivative of natural log of x. I don't get a log anymore, I get 1 over x. It's like it's simplified in some way. Right. So all of the inverse trig functions, when you take their derivatives, you actually get what are called algebraic functions. They're no longer trig. I don't know if you ever used these words before. Trig functions like inverse tangent, tangent, sine, and then also exponential and log, or what we call transcendental functions. Transcendental function means you can't write it just using arithmetic type operations. Whereas here, this is algebraic because it's purely arithmetic. Take number 1 divided by 1 plus x squared. All that is basic arithmetic operation. Sine, cosine, all the trig functions, you can't do that. So it's a little weird that sometimes the derivative ends up being much nicer than the original. So how could we prove this? So we're going to use the same trick we mentioned yesterday after I come up with this formula. So I mentioned this in passing, so I mentioned or people mentioned in the reflection, they'd like to talk about inverse stuff more. Inverse always works out nicer than we expect. What do I know about inverse tangent of x? If I plug it into tangent, they undo each other, right? So if I take that idea and now simply take the derivative of both sides, so using implicit differentiation, I would get this. So what's the derivative on the left? We know the derivative of tangent is secant squared. So how would I find this derivative? The outside thing is tangent, right? I have tangent of a bunch of things. So I need a derivative of tangent. The derivative of tangent is secant squared. But then I have to plug in this part, right? So then what's the rest of the chain will say?
You have to multiply by the derivative of the inside.
Multiply by the derivative of the inside part. So I had this part inside, so I need to multiply by its derivative. Alright, so that's the derivative on the left. What about on the right? Just the 1. So what we did is we came up with the formula. The derivative of inverse tangent of x is 1 divided by secant squared of inverse tangent of x. Which is definitely not the one you memorized. It is a correct formula, it just doesn't look as nice. So where in the world did the rest of this come from? Okay. So what is inverse tangent of x? So anybody remember doing these right triangle problems where it was like plugging in inverse thing, take sine or cosine of it, now you get this other value? Probably not. That's not pretty kind of way from you know. It's one of these random tricks we do with big things. So let's say I want to simplify this. What does it mean when you take the inverse trig of something? What is your output? Big question. When you do trig, what do you plug in? You plug in angles, right? So like I need sine of an angle, tangent of an angle. So then, if I plug in an angle initially for a trig function, what does the inverse trig function do? It says plug in something, what do I output?
An
I
angle?
output the original angle that I care about. So because I plug in an angle for tangent, what does inverse tangent do? It outputs an angle. That whole flip xy coordinates. What I plug in here is angle, so what I get out of inverse would be the input of my original, so it'd be an angle. So what is inverse tangent of x? This is some angle, call it theta. Inverse trig functions give me angles. So then, what do I know about theta? Well, tangent of theta must be x. Tangent. What angle did I get? I got the angle where tangent of that angle was my x value. That's how we think of inverse tangent. What does inverse tangent of x mean? It means find the angle where tangent of that angle is x. And then think of this as x over 1. Why would I do that? Now we're going way back. How did you probably initially learn tangent in terms of right triangles?
Cosine over
Cosine over sine over cosine. Hypotenuse over adjacent. Maybe. Think of this as the, sorry, not opposite over adjacent. Think of it back as opposite over adjacent. When you first learned sine, cosine, tangent, you probably learned it in terms of right triangles, so like opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent, things like that. What do I know about this angle? Tangent of theta must be x divided by 1. The opposite leg must be x, the adjacent leg must be 1. So I don't know what that angle value is, but if I take tangent of it, I should get this leg divided by this leg. What would my hypotenuse be?
X. X.
So what do I know? I know this value squared is that squared plus that squared. That leg would have to be the square root of 1 plus that squared. I'm going somewhere with this eventually. So, if this is theta, what I really want to know is what is secant squared of theta, right? We said this derivative formula, I need to know 1 over secant squared of inverse tangent of x. I said replace inverse tangent of x with the angle theta. This is some angle. But to use this formula, I need to know what is secant squared of that. What is secant? One over cosine? So what is 1 over cosine of theta in this triangle? Cosine of theta is adjacent divided by hypotenuse. So if you 1 over that, it's hypotenuse divided by the adjacent. This was secant squared, so whatever I get, square. So what would that be? What's my hypotenuse? Square root of 1 plus x squared divided by my adjacent leg. My adjacent leg is 1, and I square it. What do I end up with?
One plus x squared.
Yeah, square root goes away. 1 squared is 1. That goes away. I just get 1 plus x squared. So what happened? We said the derivative of inverse tangent is 1 divided by this value. But what is this value? That is the same as secant squared of some angle theta. When I set up what that angle theta is, secant squared must be 1 plus x squared. So I end up with 1 plus x squared. So it works out. There's a lot more going on with inverse. But, so like using the formula we had last time, you always get to something like this. And then think back when you were in pre-cal, you would do things like simplify this expression. When you simplify this expression, you get to 1 plus x squared. All the trig kind of undoes itself. Why would it make sense for the trig to undo itself? This says start with x. That links to some angle. And now plug that angle in here. So it's like go backwards and then go back forwards. They undo each other. I don't just get x. If I had tangent here, I would get x. Because tangent of tangent inverse, they cancel. Instead, I have secant of tangent inverse. So they don't quite cancel, but I just get the 1 plus x squared. Basically, this goes away to where it's something based only on x. Some pre-cal you thought you would never need. Like you did that for a whole test and then probably moved on and you're like, I'll never use this again. And you still may not, because we don't ask you to do this, we just say memorize the formula. But all these random things you learned at some point, they do all show up in calculus. Any questions on that one? My hint of you could always come up with these formulas for the trig ones. Technically, you could also come up with formulas for the inverse trig, but it's way more effort. All we used there, though, was what is the derivative of tangent, which was secant squared, and that's something we could come up with using just the rules we knew. Alright, so that's the background for people that didn't want to read all the background in the book. Yes?
Could we also, in theory, come up with it like the inverse tangent function from the inverse sine and cosine?
Yeah, we can do a similar trick for cosine, sine. They don't work out the exact same, but they would work out similarly where you draw your triangle and you can link it back. What am I really doing when I draw this triangle? We said you could use these to come up with the hypotenuse. That actually is kind of like Pythagorean theorem. So you could just do this all with Pythagorean theorem and never draw triangles. But we can derive all of them similarly. This is the only one that works out the easiest. Because others you have to worry about, you can't plug in certain angles because you divide by 0. And some other technicalities. Alright. We're supposed to teach y'all how math works, so that's more how math really works. We build it all up from the ground. And then all you do is memorize some formulas and use them. That was our math appreciation for 30 minutes. Alright, let's do some examples. So I just want to find the derivative. The first one, e to the sine of 3x, or 3x. This is looking much more like your quiz or your exam. We can just throw in lots of random functions with exponentials, trig, everything else, and then say find the derivative. We have all the rules, all the formulas that we need at this point. Now it's just checking, do you know how to use the formulas and the rules at the right time? So how would I find this derivative? No. So if you'd asked if we take the natural log, that is something that a lot of students like to do, because we're algebraically, how do you get rid of an exponential? So if I have something like e to the 3x equal to 4, how would you solve that? Take log, you get rid of the e. It's like if I'm solving an equation, how do you get rid of exponentials? You take a log. Here, I'm not solving anything. I want to simplify. So I want to say I want the derivative, so I need to do find d dx of this input, this function. There's nothing that said equal to, nothing to solve. So my logarithms undo exponentials, but I'm not trying to undo the exponential. I'm trying to find its derivative. I change the context here. Yes?
Wouldn't we do the chain rule?
Yes, I would need a chain rule. So what do I know? I know the derivative of e dx is e dx, right? My goal is to get rid of the dx. Whenever we say take the derivative, if you set up your first line as f prime is d dx of f, the rest of the goal is simply get rid of d dx. So first thing I do is, this is an exponential, so I just use the one formula I need. What is the derivative of e dx? It is itself, right? But then what's the catch here? What's the difference between that one and this one? Here I only had x in the power. There I have a bunch of other things in the power that I ignored. I can't just ignore it. That's where the chain rule comes in. Because the power wasn't just the value x, I have to multiply by this part. So that's our chain rule. Technically here, we never write this. But so you could do the chain rule every time. What's the derivative of x? 1. So you could technically write it there every time. d dx times 1 is d dx. You could always do the chain rule, and then if you didn't really need it, it kind of disappears on its own. All these rules have to be consistent with each other. Alright, so now we got this, now what? So this part I am completely finished with, right? It's never going to change, there's no more d dx there. So now I need to know what is the derivative of sine of 3x. Okay. So what's the derivative of sine of x? So that is cosine of x. So here I'd say the derivative of sine must be cosine. But I wasn't plugging in x, I was plugging in 3x. So I need to chain rule again to now multiply by the derivative of 3, or 3x. Because I wasn't only plugging in x, I need to put this last piece on there. So I had the ddx here. Then I got to here, which was a little bit more simple. I had less going on. Now I just need, what is ddx 3x? 3. Slope of 3x is 3. Am I done? There are no more ddx symbols. That means this is the derivative. It's always look where ddx is, see what rule I need to do next, and just keep writing it until you get to a point where there's no more ddx symbols. Right. Number 2. Find the derivative of secant inverse of 2x plus 3. This one's a weird one. What is the derivative of secant inverse? This one looks weird. One over the absolute value of x times the square root of x squared minus 1. Derivative of inverse sine is 1 minus x squared, so I just remember it switches for this one. You need this one random absolute value. Anybody know why there's an absolute value here? Technically it was this. How do you, what is the square root of x squared?
X.
You always want to say x. It's technically the absolute value of x. Why is it an absolute value?
Because you don't take the negative.
Square root is always a positive number. Like if I say what's the square root of 4? 2. Technically negative 2 squared is also 4. But you never write the negative one. So because we need this to be, because we can't have this being negative, so you take the square root of x squared, you have to put the absolute value on it. That fixes this positive negative issue, which is where this gets factored out this way. Alright, that's the second one. So what's the derivative here? I would use that formula, but I'm plugging in 2x plus 3. So it must be 1 over this. Why is this formula kind of a pain? I wouldn't say a pain, it's a little different than some of the others we've had. What does it mean to plug in 2x plus 3? That means everywhere I had an x before, I need to write the entire input. So I can't just say, put 1x here, then 2x plus 3 in here. Everywhere I had an x, I need to write all of 2x plus 3. And then because this had something attached to it, the last step would be multiply by the derivative of the inside part. Step 2 the chain rule, right? Does that one make sense how it ends up being that formula? Take our formula, anywhere I had an x, right, 2x plus 3. And then because I was plugging in 2x plus 3, the last thing is the chain rule where you multiply by the derivative inside. But this one looks strange in some sense. It's easy to make a mistake on this formula where you don't plug in everything everywhere. This is one I've seen messed up a lot. So what do I get? What's the derivative of 2x plus 3? 2. I've got rid of all the dx symbols. So I'm up. Or like, when did you find the limit? Once you plug in, you can stop writing the word limit. Any questions on that one? Number 3. Find the derivative of e to the x times tangent of x. What rule do I need? Yeah. So like I know I need the derivative of e dx, I know I need the derivative of tangent of x, but when I look at that, the problem is they're both multiplied, right? So to start, I need a product rule. So the product rule says first one times the derivative of the second plus the second one times the derivative of the first. So I end up with derivative of tangent is secant squared. Make sure you're writing of x every time. Like you have to include the input. Plus tangent of x times derivative of e dx is e to the x. So have you done?
Mm-hmm.
In theory, I can maybe try to factor out and make this look nicer, but there's no need to in this section. A couple things that just kind of words of warning. What would this be? Yeah, it really doesn't make sense. Why does it not make sense? It says my variable is x. Where's the x? So writing something like this equal to this really doesn't make sense. Or you have to be careful with how you do it. It really needs to be of x for both of these. We're saying the derivative with respect to x, there needs to be an x there. One place I see this is this happens, and I really don't want y'all to do this. But it's kind of the same idea. Does that make sense? Of course, now I wrote it, I'm not going to write it because I wrote it on the board, must make sense. When you see sine of 3x, does that mean sine times 3x?
No.
No. This is plugging 3x into here. So this is an input, not a product. You can't treat it like a product. 3x is being plugged into the sine function. They go together. Whenever you write, the book sometimes writes things like, you see it more on stuff like this. It's not sine times 3x. What they really mean is sine where you plug in the value 3x. The book drops parentheses a lot of the time, and technically you're allowed to drop parentheses for the trig function. but we still mean you're plugging in this value into this string function. You still have to treat it like an input. Okay? Make sure you're not reading these quickly and missing that. I've also seen it a lot with natural log. When you say natural log x, you mean natural log of the value x. If you read it of, so log of x, sine of 3x, what rule would you need? You say of something, it means you're plugging something in, right? That now looks like a chain rule. If you read it out loud, or read it to yourself correctly of sine of 3x, that means you need a chain rule because you're doing something, you're plugging something into something else. When you say of that, it's not sine times 3x. Right? People forget the chain rule on these and want to use things like product rules or different things. And a lot of it's the notation. We don't need parentheses here, but you can always rewrite the problem with parentheses. I basically use way more parentheses to make sure I don't misread it. That's just a place I always see lots of points. Any other questions so far? This is both the shortest section and the most intimidating because here's a list of 20 formulas. All right, let's find the derivative of 5 times log of x plus 1 divided by sine of x. What rule do I need first? Actually, that's a trick question. There's 2 rights. There's 2 good ways to do this one. Before we do that one, this was on the quiz last time, and I want to mention it. Almost everybody did the same thing here. If you want to find the derivative of 7 divided by x, what rule do I need?
You could use the chain rule. Chain rule.
Yeah, almost everybody did quotient rule. I might be lazy. I tried to find ways not to use the quotient rule.
I tried to do it.
I did the chain rule.
And then I wasn't entirely sure if I got it right, so I tried to do the quotient rule.
That's like saying 7 times. Oh, this is. I'll mention this one first too. I could do a product rule here, but remember this is a constant. So you could factor the 7 out. You can't factor out anything with an x. But if it's a number, you can factor it out. So that's going to show up here, right? I could write this as 5 times the derivative of natural log of x plus 1 over sine of x. I can move the 5 out so I don't have to track it through the whole problem. Could do that here. How do I avoid the chain rule here? Yeah, that's the same as x to the -1 power. So then what's the power rule say? Bring down the -1, subtract 1. I don't need the quotient rule. I think 3/4 of y'all use the quotient rule for that. You don't need to. So thinking about the quiz or the test, remember the things we really like are the power rule. Why do we have logarithmic differentiation? So we could get rid of all the products and everything and make it just these simple rules over and over. Why would you do something like this? So we can make it just a power rule and not have to deal with the quotient rule. Your go-to shouldn't always be what's the biggest rule I could use. It's could I simplify this a little first to make it easier? That's not one we always talk about, but there are problem solving strategies there. Usually, what we would say is algebra first, calculus second. Is there a way to simplify the problem before you start doing big calculus ideas? Before you start using every rule possible and using lots of work, is there a way to simplify it first? Alright, this one we can't really simplify. So what do I get? So I pulled the 5 out, so the 5 is just going to sit here by itself always, right? But it's 5 times everything else I do. So I have to use a quotient rule, so that's bottom function times the root of the top function minus the top function times the root of the bottom function, all divided by the bottom function squared. So I get 5 times sine of x times what's the derivative of natural log of x plus 1? Hopefully y'all just turn in this homework so you've done these. Or the log part lots of times.
1 over x plus 1 times 1.
The derivative of log of x is 1 over x. So this would be 1 over the inside part times the derivative of the inside part. And then minus natural log of x plus 1. What's the derivative of sine of x? That becomes the function cosine of x. And then divided by sine squared of x. A lot of times we put the exponent there. So I had one more derivative. What's the derivative of x plus 1?
1.
Just 1. Alright. Am I done? I did the quotient rule. Quotient rule told me these new derivatives I need, like the derivative of natural log. 1, I did that. I've gotten rid of all the dx symbols. So this is the answer. I could, in theory, simplify it some, but we're not requiring that. Yes?
Where did you get cotangent from?
Yeah, that's really bad looking cosine.
Oh.
Any questions? Just a lot more practice. Practice these is definitely do the homework. Practice taking derivatives a lot on the skills problem. Most of the test, most of the quiz is can you take a derivative correctly? If you notice you didn't do well on the quiz, look at the mistakes you were making so you don't make them again on this next one. The next quiz is going to be very similar to the other one, where it's a lot of take the derivative. We need to make sure we have this skill down. The chapter 2 test should be very straightforward in some ways.